A la seva dreta està la doctora Carmen López Díaz, que és del Departament de Química i Tecnologia de los Alimentos de la Universitat Politécnica de Madrid, i jo mateix, que sóc el doctor Francesc Valero, d'aquí del Departament d'Enginyeria Química, Biològica i Ambiental de l'Autònoma de Barcelona. L'acte consisteix en una presentació del Gerard d'uns 50-60 minuts, més o menys. A continuació, el tribunal farà les preguntes que consideri oportunes, amb un temps no limitat, però que també intentarem ajustar-nos a un temps raonable. I posteriorment, preguntarem finalment si algun membre doctor del claustre de la UAB té alguna pregunta a fer. I en aquest punt és quan tancarem l'acte públic perquè el jurat deliberarà la qualificació que posarà el Gerard. Posteriorment, tornarem a cridar tot el personal, donarem la qualificació pot ser de no apte, apte, notable o excel·lent, i en el cas que tot el tribunal decideixi que per unanimitat és excel·lent, hi ha la possibilitat d'aconseguir un cum laude, que és un vot secret del tribunal, i que per tant el Gerard i els seus directors, si els servís al Gerard, perquè si no li avisen a ningú, sabran d'aquí a 2 o 3 dies si té la qualificació del cum. Dit això, I try again to English, and now is Marielle, the chair director of the system.
So, as it was said, Gerard Masdeu, you have 15 to 1 hour to present your work, and then we will start with the questions. So, time is yours.
Okay, thanks for the introduction. So these are the content of this presentation. I'll start with a brief introduction to the topic, follow with the objective of the work, and then present the main results of the work divided in 5 chapters. And I'll finish with the overall conclusions. So first of all, the introduction, and I'd like to start with general aspects of biocatalysis. So biocatalysis is the use of enzymes for the transformation of natural and non-natural compounds, and in comparison to a chemical process, it uses enzymes instead of solvents, and these enzymes can be recycled, and non-hazardous waste is formed after with the reaction. But the problem is that the enzyme can lose its activity by reversible unfolding of its structure, which is called denaturation, or irreversible structural chemical changes, which is inactivation. So we have a reaction, we have a biocatalyst, but we have to think about, is it suitable for the reaction? And we will think about, we'll evaluate this in terms of activity, stability, specificity, and selectivity. If we consider that it is suitable for the reaction, we can proceed with the biocatalytic process development and continue with the biocatalyst characterization, downstream, and economics. If it's not suitable, we have to improve this enzyme by reactor or reaction engineering, protein engineering, or physicochemical changes, physicochemical methods, such as immobilization, and we will focus on this later strategy. So, immobilization is the physical confinement or localization of the enzyme in a defined region of the space with retention of their catalytic activity. And there are many factors to consider, such as the structure of the carrier, the distance between the enzyme and the carrier, also the functional limitations, but we will focus on the principle of the immobilization method. There are many methods in the literature, but the methods that have been used in this work are absorption, also covalent binding, and affinity. And the last term to clarify are the cascade reactions, which a cascade reaction is a sequential of reactions in which the product of one reaction serves as a substrate of the next one. And it can be performed in consecutive reactions or in one-pot reaction. So now we have to talk about our topic, which is the synthesis of aminocyclitols. These compounds are sugars with a nitrogen atom in place of the ring oxygen atom, and they are glycosidase inhibitor with therapeutic potential, so they have been evaluated as antibiotic, antimetastatic agents, and so on. But we will focus on one aminocyclitol, which is D-fructose, which is a nutraceutical that has shown important potential in the treatment of diabetes. So this is our compound D-fructose. which can be produced with this precursor here, and we will focus in this compound in this precursor. To synthesize this compound, there are many ways, but one of them is aldol addition, which is a powerful tool for the reversible formation of carbon-carbon bonds. It yields an antipure multifunctional molecules from simple starting materials, and it is catalyzed enzymatically by aldolases. These enzymes can be classified according to the mechanism in class 1 aldolases or class 2, and also according to the structure to the donor substrate. The most used aldolases probably are DHAP-dependent aldolases, and these enzymes have strict donor substrate specificity towards DHAP. So at the end, you have this phosphate in your final product, so you have to remove it with an additional step. So it would be better to use DHA, an aldolase that uses DHA. This is the case of D-fructose-6-Phosphate aldolase, which is a class 1 aldolase from E. coli, and it catalyzes the formation of cleavage of fructose-6-phosphate using DHA and glyceraldate phosphate. So we can use this enzyme for the synthesis of the phagomin and for the prephagomin, which is the precursor, and it has already been used in the literature to catalyze these reactions. In one publication, two mutants of these enzymes were employed, and this single mutant FSA showed a better results in terms of productivity. So we can use this enzyme to catalyze this reaction, so we can get the prephagomin. So, okay, now we have to synthesize this aminoaldehyde. And how to do it? There are many publications about chemical oxidation of alcohols to aldehydes, but with low selectivity and high cost of oxidizing agents. So this reaction is advantage to be as an enzymatic process. We can find examples in the literature with alcohol oxidase, lacase, coupled with tempo, but some of them show low selectivity towards the aldehyde. Also, we can find reaction catalyzed by host liver alcohol dehydrogenase, but it uses cofactor. So, as an alternative, we present the use of Chloroperoxidase to catalyze this reaction. This enzyme is a peroxidase that catalyzes the chlorination of monochlorodiimidone in vivo, but also catalyzes halide-independent reactions, such as the alcohol oxidation. This enzyme does not require a cofactor, but a peroxide, but the problem is the use of this peroxide can inactivate the enzyme. And we will study this inactivation along the work. So with this enzyme, we can do this oxidation of the beta alcohol to the beta aldehyde and couple the FSA to get the prephagomin. So what is the main objective of the work? Is the feasibility of a multi-enzymatic cascade composed by a peroxidase and an aldolase for the synthesis of immunocyclitols using amino alcohols as a starting material, and in particular the synthesis of prephagomin. And the specific aims are these 5 that corresponds to each chapter of results. We will investigate the substrate specificity of CPO using amino alcohols as starting material. Also the solubility and the suitability of this enzyme for the beta alcohol oxidation. We will identify the bottlenecks in the coupled reaction, and then 2 methodologies are proposed: a kinetic modeling of the overall reaction and the mobilization of both enzymes. And finally, I'll finish with the model exploitation to find the optimal operating conditions. So let's start with the first chapter of results. It is about the oxidation of CPO catalyzed amino alcohols. Yep. So before talking about the oxidation of beta alcohols, it is worth to investigate the substrate specificity of this enzyme regarding amino alcohols. That has there's not much data in the literature. and is especially restricted to alpha amino alcohols. So the oxidation of various amino alcohols is intended, analyzing initial reaction rate and the stability of the enzyme. So we have this block of results in this chapter, and another block is the oxidation of the beta alcohol, which is the first step in the prephagoamine synthesis. In this reaction, the substrate solubility is a limiting step, so the use of organic solvents is considered, and then also the operating conditions prior to coupling are investigated, which are the reaction medium, initial substrate concentration, and the peroxide nature. So we will start with the first block of this chapter, which is the oxidation of amino alcohols. And these are the amino alcohols that were used, up to 8 amino alcohols with similar structure, but they differ in the amine carbon configuration from alpha to epsilon, which is the position of the amine group to the hydroxyl. Also, some substituents in position R1 were used, and some also substituents in position R2. This position corresponds to the amine protecting group. That is important because when we have the aldehyde, if we don't have the amine protecting group, this compound can cycle. So these are all the amino alcohols that were used, and this reaction was performed in a biphasic medium using semi-continuous addition of the peroxide in order to maintain this concentration at the low level to reduce the inactivation of CPO. The reaction was monitored following the activity of CPO according to a spectrophotometric test, and the substrate and product concentration were followed by HPLC analysis. And regarding the results of this block, here the table of all the amino alcohols oxidation is presented. We have all the compounds with the initial reaction rates and stability of the enzyme according to the use of one peroxide or other. We use hydrogen peroxide to catalyze the reaction, and also terbutyl hydroperoxide. So, if we compare the structure of substrate 1, 2A, 4, and 5, their structure is similar, and they only differ on the position of the amine group. So, now we saw that the further the amino group from the hydroxyl, the lower the initial reaction rate. If we compare to A and to B, we saw that the presence of the amino protecting group lowered the initial reaction rate in both cases. Also, when analyzing the oxidation of a compound number 3, with the substitution is FMOC, which is a bulkier group, we observed that no oxidation was occurring. If comparing to B and to C, this extra methyl substituent in position R1 alter the initial reaction rate depending on the oxidant. And when analyzing the oxidation of to D, no conversion was observed because of this substituent. And finally, regarding the oxidant selection, we saw that the operational stability of the enzyme was similar or higher when using hydrogen peroxide instead of terbutyl hydroperoxide. So now let's move to the second block of this chapter, which is the oxidation of the beta alcohol. This is the reaction, the oxidation of the beta alcohol to the beta aldehyde, and the reaction operation was similar than before. So this is the reaction scheme that was proposed at the beginning of the reaction. We have 1 mole of alcohol converted in 1 mole of aldehyde, and then we get 1 mole of amino acid. And these are the operating conditions that were studied: reaction medium, substrate concentration, and the peroxide. So regarding the reaction medium, as said before, the solubility of the alcohol is limiting in this medium, in this reaction. So we use several organic solvents, and we saw that the initial reaction rate was higher when using the acid buffer, and finally we chose this medium for the reaction. And regarding the concentration of the alcohol, no substrate inhibition was observed in the solubility range. So finally, the initial substrate concentration was fixed was set at the maximum solubility. And regarding the peroxide selection, we tried these two peroxides for the reaction, and we observed that the inactivation of this end of the CPO was lower when using the hydrogen peroxide, but the initial reaction rate was lower with this peroxide. So we have this compromise between stability and reaction rate. And this was the scheme proposed at the beginning of the reaction, but when analyzing the moles of substrates and product, we observed an imbalance. So this scheme was discarded, and another scheme was proposed taking into account a chemical reaction between the aldehyde and the peroxide. If we have terbutyl hydroperoxide, we have one byproduct, and with hydrogen peroxide, we have two byproducts. This scheme was experimentally validated, and also with HPLC, MS, and NMR analysis. Finally, we did a reaction with higher amount of CPO to see the extent of the reaction. And we achieved height conversion, 90%, almost 90%, but low beta-aldehyde yield because the product selectivity was in favor of the acid. So this chapter has studied the substrate specificity of TPO and solubility for the beta-alcohol oxidation. And these are the conclusions of the chapter. The CPO amino alcohol oxidative capacity have been studied. We saw that in this enzyme accepted configuration alpha to epsilon, the farther the amino group from the hydroxyl, the lower initial reaction rate. And also we saw the effect of amino protecting group and other substituents, and the stability of the enzyme that is higher with hydrogen peroxide. And the beta-aldehyde synthesis has been studied also, determining the operational conditions and identifying some byproducts. Also, we saw that the selectivity of the beta-aldehyde is quite low. These results were published in the Process Biochemistry journal and also in the Data and Brief journal. So let's move to the second chapter of results, which is about the first assays on the of the coupled reaction. So now we have to study the operating conditions of this reaction, and we will take into account the peroxide. We saw this compromise between stability and initial reaction rate, and we have to study the buffer. The buffer determines the stability of both enzymes because we have pH dependence. In the literature, we can find that the CPO is stable at the pH between 4 and 7, and the FSA between 5 and 11. So a theoretical reaction pH would be 5.5 to 7. And we have to study also the substrate and enzyme concentrations. And what happens in a one-part synthesis? That we couple the FSA reaction, and it can reduce the formation of the amino acid. Also, we have an unknown behavior of byproducts from the chemical side reaction, and we can have constant inhibition from substrates and products from all the reactions. And also, of course, the inactivation of both enzymes. We've seen the inactivation of CPO caused by the use of peroxide, and also FSA can be inactivated from any reagent. So regarding the reaction operation, in this case, the peroxide was added in one pulse, and the substrates and enzymes were mixed according to the variable to study. We want to study the peroxide, we will mix the buffer, the peroxide, the alcohol, and the enzyme. We will also study the pH by incubation of the enzyme in buffer. Also the enzyme compatibility between CPO, FSA, and incubating with peroxide. And finally, we did the coupled reaction. The reaction was monitored also with the CPO activity and the HPLC analysis for the substrate and product concentrations. The FSA activity was measured with this spectrophotometrical test, and the FSA was produced in our lab by fed batch fermentation using a plasmid that was supplied from Professor Peraclapes. And after fed-batch fermentation, the enzyme was, the cells were disrupted and the enzyme was purified using haystack purification. And okay, let's move to the results. We have to talk about the peroxide selection. We will have this reaction, which is the oxidation of the alcohol, and also we will have these side reactions. And these two peroxides were tested. In this case, when using the hydrogen peroxide, no conversion of the amino alcohol was observed, in contrast to the first chapter. The difference is here, just one pulse of peroxide was used instead of semi-continuous addition. So we assume that this one pulse, all the peroxide was degraded because a lot of bubbles came up in the reactor. But however, when using the terbutyl hydroperoxide, we detected a conversion of the amino alcohol and also inactivation of the enzyme again. So this the activation should be characterized, and we did choose this peroxide for the following reactions. Regarding pH stability, we saw that the CPO was stable between a pH of 5 till 7, and FSA was stable along all the tested pH. So the reaction can be performed at the pH range of 5 till 7. Regarding enzymes compatibility, when incubating both enzymes in buffer with the presence of peroxide, we observe, of course, the inactivation of the CPO, but surprisingly, we observe that the FSA was inactivated. So, is this inactivation caused by the CPO or because of the peroxide? If we incubate both enzymes together, no inactivation was observed, and when incubating with the peroxide, also no inactivation was detected. So, this inactivation of the FSA should be caused by the use of peroxide and chloroperoxidase together. This inactivation should be characterized, and we also observe some precipitation of the FSA at pH 5 till 6. So finally, the buffer and pH for the reaction was this one, pH 6.5, and this was selected for all the other reactions. We also did a couple of reactions of this reaction of the CPO and the FSA, also including these side reactions and activation of those enzymes. So we did this a couple of reactions, but however, although a high amount of the FSA was used, no prefagum information was observed because the inactivation of the FSA. And comparing this reaction, this couple reaction with a control reaction without the FSA and the DHA, we observed that the peroxide was degraded by the CPO, and also that another side reaction was present involving the DHA, probably a DHA oxidation catalyzed by CPO and peroxide. So we have a complex system, and okay, we've identified the bottlenecks in the couple reaction. We have selected the terbutyl hydroperoxide as peroxide for the reaction. We have selected the buffer and pH. We have detected the inactivation of CPO and also FSA, and also two side reactions are identified. The degradation of the peroxide and probably an oxidation of the DHA. So, yeah, and no yield of prefagomine was obtained, or almost no yield. So, two solutions are proposed, a kinetic modeling of the overall system and the mobilization of those enzymes to increase their stability. So let's move to the chapter of the kinetic modeling of the couple reaction. Complex molecules are usually produced in reactions involving more than one substrate. This is our case. With CPO we have two substrates, the alcohol and the peroxide, and with the FSA we have the aldehyde and the DHA. So consider an irreversible BP to substrate reaction. So two substrates, A and B, and two products, P and Q. Several mechanisms can be identified according to the reaction. We can have ordered sequential mechanism as FSA, random sequential mechanism, or a ping pong as CPO. For example, here we can see that the substrate E interacts with the active site of the enzyme, a product P is released, and then the substrate B enters in the active site, releasing product Q. If we want to develop a kinetic model, we have to estimate its kinetic parameters, and we can do it using initial reaction rate analysis that takes into account the initial reaction rates of reactions in which we vary the substrate concentrations, and we use linear transformations of data and linear regression. But instead also we can use a progress course analysis that we take into account the entire time course. And then more data is obtained from experiments. However, if system complexity hinders both applications. Why to do a kinetic model? Because we can simulate alternative routes of an existing process in silico. So we can speed up the bioprocess development and the control strategies design, and also find the optimal operating strategies of a complex system. So this is our reaction, the couple reaction between the CPO and the FSA. We have talked about the oxidation of the alcohol. We have also the oxidation of the aldehyde, a chemical reaction involving the aldehyde and the peroxide, a degradation of the peroxide, also the inactivation of the CPO, the oxidation of the DHA, and of course the aldol addition that catalyzes FSA, but also the retroaldol addition that catalyzes the same enzyme. And we have talked about this inactivation of the FSA, which is caused by the use of this peroxide and the CPO. And in further incubations of the FSA and DHA, peroxide and CPO, we observed that another inactivation of the FSA was occurring in our system. Part of these results were have been done in collaboration of the University of Zagreb. So I'll try to present step by step how this kinetic model has been developed. First of all, we incubate together the CPO and the peroxide, and we will have these two reactions. Okay, so because we have to try to separate all the reactions to study the medium. Okay, so we do this first, then we will study the chemical reaction. Then we have the oxidations of the CPO, and which is the oxidation of the alcohol, aldehyde, and DHA. And these three reactions have one parameter in common, which is the affinity of the enzyme to the peroxide. So these three reactions were studied together in order to get an estimated value of the kinetic parameters to be used as initial value for the iterations with the model, with the software to get the model. With this initial value, we studied this oxidation of the aldehyde, then we add this alcohol, and we study the oxidation of the alcohol involving also all the other reactions. We studied the oxidation of the DHA, and then we put everything together to see if there's some cross inhibitions between these reactions. And with this, we have all the kinetic model for the CPO catalyzed reactions. We also developed a model for the FSA reactions, studying the aldol addition, aldol additions, and inhibitions between these two reactions. And finally, we studied the inactivation of the FSA. First, the inactivation caused by the peroxide, and then the inactivation caused by this oxidation of the DHA. And with this, we have the model, okay? And these are the mathematical expressions that have been used. The reaction operation was similar, and these are the software used for this, this estimation of the parameters. So I going to present one example of this methodology, and in order to not extend the presentation. Okay, so if we incubate the CPO and the peroxide, we can study this degradation of the peroxide and the inactivation of the CPO. So this is the experimental distribution of all the experiments. And with the experiments, we propose these two equations for the degradation of the peroxide, as sigmoidal behavior was observed, and for the inactivation of the CPO, it was expressed as a degradation of the peroxide, so as a function of this equation. With this, we simulate experiments, and the model was able to predict the data. And we got the kinetic parameters, and we evaluate for possible inhibitions. So this was done for all the reactions that I have shown before. And finally, we get the kinetic model involving all the 7 reactions and the 3 inactivations. And we have all these reactions here, and some inhibitions were observed. Cross inhibitions, for example, in the oxidation of the alcohol, we observed some inhibition of the DHA, and also competitive inhibition of the alcohol in the DHA oxidation, and so on. And now we have a model, but we have to validate it. And with this, to do this, some experiments were performed, experiments that have not been used to estimate the parameters. So we use all the equations, and as we can see here, the model predicts the data properly. These are some some experiments. So we have we have done this kinetic modeling of the reaction, separating each reaction to study its kinetics individually. Up to 7 reactions have been investigated, and to develop a kinetic model and do this validation. So we have to further study the enzyme immobilization to increase the stability, and finally we will continue with the exploitation of this model. So let's move now to the immobilization of both enzymes. Okay, of course, there's no universally applicable method for immobilization. So the selection of the immobilization procedure depends on the enzyme characteristics, the support characteristics, and also the attachment that we want to perform between the substrate, the support, and the enzyme. The immobilization efficiency is analyzed in terms of the immobilization yield, which is the enzyme mass that has been immobilized in a support, and also the retained activity that corresponds to the activity of the final derivative. Regarding the immobilization carrier, its structure also influences the immobilization process, so because it determines the biochemical, mechanical, and kinetic properties of the immobilized derivative. 2 carriers were studied, the agarose and magnetic nanoparticle clusters. Let's start with agarose. The specific features of the agarose are well known, and this support is very used in immobilization because its functionalization can be easy because of its numerous hydroxyl groups on the surface. 2 functionalized agarose supports were used. One was amana agarose, which is agarose functionalized with amana groups in the surface, and it was used to immobilize CPO, and coida agarose, which is agarose functionalized with iminodeacetic acid that we can chelate the metal in order to immobilize the FSA. And regarding magnetic nanoparticle clusters, we know that magnetic biocatalysts are easy to separate from the reaction medium just by applying magnetic field. And superparamagnetism, that is, we have to understand about superparamagnetism, that is the dispersion into a liquid reaction medium, so we don't have agglomeration. So these superparamagnetic particles are very used in biotransformations because they have easy recovery and homogeneous catalysis. But the problem with this easy recovery is that the strong magnetic force should be used in order to retrieve all the nanoparticles, because they are very small and the magnetic force depends on that. So, if we assemble these nanoparticles into magnetic nanoparticle clusters, we increase this surface, this volume, and maintain the supermagnetic nature of the individual nanoparticle, and then we have effective manipulation with the magnetic field. This is one nanoparticle, and this is a cluster of nanoparticles, but I'll talk about this later. Part of the results were done in collaboration with the Enzymtic Institute, and these are the functionalized carriers that were prepared: mana-agarose, coida-agarose, and these magnetic nanoparticles that were prepared by this group from the Enzymtic Institute. And regarding the monetization of immobilization, we analyzed the immobilization efficiency in terms of the yield and activity by measurements of the suspension and the supernatant. The activity of CPO was followed by monochloroimidone chlorination, and the FSA with the spectrophotometrical test that was presented before, and also by a new activity test that was developed, but I'll present this later. And the substrate and product concentration that were followed by HPLC analysis. So, okay, we'll talk about the immobilization of CPO and FSA. So let's start with the CPO on mana-agarose, and then I'll talk about nanoparticles. So this is the immobilization of CPO on mana-agarose, and this immobilization has already been performed in the literature. But however, we wanted to use this derivative because in the literature, increased stability of the enzyme is presented. So we adapted the protocol and studied the concentration of carbodimide, because we need carbodimide to do a covalent bonding between the amino groups of the surface to the carboxylic groups of the enzyme. We studied the concentration and also the incubation time. And after this adaptation of the protocol, we did the beta alcohol oxidation using soluble CPO and immobilized CPO, and we did the comparison, and we saw that the enzyme immobilized on agarose was higher stable, but it showed a lower initial reaction rate because of the functional limitations. However, as the enzyme was stable during more time, higher alcohol conversion was obtained. Regarding the mobilization of magnetic nanoparticles, of CPO magnetic nanoparticles, I'd like to present how this was done. We have the preparation of the clusters. One nanoparticle, cluster of nanoparticles, silica-coated magnetic nanoparticle cluster, and then it can be functionalized with several groups on the surface. The enzyme can be also modified in order to add some functional groups on the surface to perform the immobilization. We have the native enzyme, and also with aldehyde groups and other modifications. Then we mobilize the enzyme, and after the screening, we select the most promising derivative, do a further study characterization, and a final selection of one derivative that we will use in the beta alcohol oxidation. So let's start with the screening of the immobilization of native CPO, non-modified CPO. This is the table of results. We have here that the many clusters were used with different functional group on the surface in order to attach different functional group in the surface of the enzyme. This immobilization was done non-covalent or covalent, depending on the case, and this is the result in terms of yield and activity. If we analyze this in number 3, this immobilization was done non-covalent with high yield and retained activity. We further studied this immobilization. We determined the maximum CPO load, and we confirmed that there was no limitations in this case. And as we can see here, the enzyme was attached very fast to the nanoparticles, retaining its activity. We also did this immobilization trying to get a covalent bond between the enzyme and the support. but some activity was lost with this covalent binding, so we tried to improve this immobilization by a two-step procedure using a prior ionic immobilization. So we do ionic incubation, and then we add this carbolimide to perform the covalent binding. And we managed to increase the activity of the final derivative. If we analyze now the number 6, we have no activity here because we are touching to these amino groups on the surface, close to the active site, and we try to improve this immobilization also by two-step procedure and other alternative, but however, non-covalent bonding was obtained. In number 7, although no activity was present here, I like to mention this immobilization because we will do an alternative to this. We will try to do it the other way, so which means to immobilize through the through the aldehyde groups on the enzyme to the amino groups on the magnetic nanoparticle cluster. But I'll talk about this later. And finally, a surprising result were obtained with immobilization on the alpine functionalized nanoparticles, and we studied the enzyme load, and finally we saw that this immobilization pushed through these hydrogen bonds, so it was non-covalent. And regarding this immobilization that I've said, is number 7, we tried to do this immobilization from the aldehyde groups of the CPO. So we have to modify the CPO, to oxidize the CPO to get these compounds, and so we did the oxidation of the sugar moieties on the surface. Then we did the immobilization with higher immobilization yield and acceptable retain activity. So we have 4 selective derivatives, which are these 4, and we did the physical characterization of the magnetic nanoparticle clusters coupled to the enzyme by zeta potential analysis, hydrodynamic size, and time imaging. So we decided first to use this derivative for the reaction, but this binding was ionic, and when incubating in reaction conditions, the enzyme was released to the supernatrium. So finally, as we require covalent binding, we chose this derivative for the reaction. So if we use this derivative, in comparison to soluble enzyme and also soluble enzyme, but with further oxidation of the sugar moieties, and we do the comparison, we saw that the enzyme was more stable after the immobilization, and that the initial reaction rate was similar in both cases. But as the enzyme is more stable, finally we have higher conversion of the beta alcohol. So it is a promising biocatalyst to be used in the couple reaction. If we move now to the immobilization of FSA, let's start the immobilization on agarose. Coida-agarose, leveraging the heat stack that has been added by genetic modification of the enzyme, we characterize this immobilization, determining the enzyme load, also checking by diffusional mutations. We achieve immobilization with high immobilization yields and high retain activity, and we use this enzyme in the DHA aldol addition. We saw similar results to the soluble FSA, as no inactivation should be occurring. And so this biocatalyst can be used in the couple reaction. And regarding the mobilization of FSA in clusters, magnetic nanoparticle clusters, the same clusters as before were employed, also a cluster with EDTA. And to determine the mobilization parameters, the FSA was too low because of its specific activity. So the determination of these parameters is different from before. Here, the yield was calculated by protein mass quantification using Bradford method, and the retain activity was performed with a new activity test in collaboration with PhD student Luis Miguel Vázquez. okay, we do the immobilization and we do a primary selection according to the immobilization yield, as we measure with the Bradford method. So up to 11 derivative with immobilization yield near or above 50% are selected, and it is worth to mention that this binding between support and enzyme is electrostatic. So, okay, we have these 11 derivatives, but we have to check if they are active or not. And after doing this analysis using this HPLC test, 5 derivatives with retain activity above 50% were obtained. But however, as said before, these immobilizations were only electrostatic, and if we require covalent binding, we have to do another immobilization. And in this case, we selected candidate number 3, because the immobilization was through the amino groups on the one cluster and the carboxylic groups on the FSA, so we can perform this covalent binding using carbonamide technology. We did this immobilization to study the proper concentration of this covalent agent, and some activity was lost, but finally we got a derivative with 30% retain activity. We tried this derivative in the aldol addition reaction in comparison to the soluble enzyme. We tried to do reaction cycles. This is the results of the first cycle of the immobilization of the immobilized enzyme compared to the soluble enzyme. There are similar results, although lower yield of prefagomine was obtained, and we observed that the enzyme was getting inactivated. So after this second cycle, almost no prefagomine yield was obtained. So we have immobilized those enzymes in order to increase their stability, and the chapter conclusions are that we have immobilized CPO on mana agarose and also in the clusters, increasing the stability of the enzyme and getting higher conversion of the alcohol. FSA has also been immobilized on coida agarose with similar results to the soluble enzyme, and also in clusters, also with similar results to the soluble enzyme. But however, we saw that the enzyme is not stable enough. So we should perform more exploitation to get the optimal operating conditions and see if we can solve this inactivation of the enzyme and get more yield of the prefagomine. Part of the results of the immobilization of CPO magnetic nanoparticle cluster were published in the Chemical Technology and Biotechnology Journal. So finally, the last chapter of results, which corresponds to the model exploitation for process intensification. So, okay, we have a model. So we can use the developed model for process intensification to evaluate the possibilities of our reaction. So in our synthesis of the prefagomine, we will use the model to study the initial operating conditions, and we will evaluate 2 reactor configurations, 1 part or 2 consecutive reactions, and we will use the enzyme as soluble form or immobilized in the selected immobilized derivatives. The reaction operation was similar than before, and it's mentioned to say that the optimization calculations were performed using the software that has been used for the model, and doing multivariable optimization and trying to maximize the yield of prefagomine if the reaction is performed in 1 part, or the yield of the aldehyde and prefagomine if they're performed in 2-step reactions. So let's start with the results regarding the 1-part synthesis. So we use the model to find the optimal initial conditions for a 1-part approach. And the variables that we have to optimize are the initial concentration of the peroxide, the alcohol, the DHA, and both enzymes. We use the model, and the model predicts the optimal conditions, this shown in the table, that this reaction will give
near 15% yield of prifagomine. We did experimental verification of these values using both soluble and CPO, both soluble CPO and FSA, and similar results were measured in comparison to the predicted values. So we saw that even when using a higher amount of enzymes, yield near to 15, only 15% was obtained. So the reaction should not be performed in one part reaction, but in two consecutive reactions in order to separate both enzymes and reduce inactivation or avoid inactivation of the FSA. So if we move now to the two-step synthesis, now we want to use two separate vessels with an intermediate ultrafiltration step to remove the CPO and reduce this inactivation of the FSA. And here the optimization procedure was different. If we want to use the mobilized form of the enzyme, we can only use 100 milligrams of support per ml. We want to maintain the 10% volume. So only 15 milligrams were used of each enzyme. So this fixed the concentration of the enzyme according to the maximum enzyme load that can be immobilized on the nanoparticle or on the agarose. And also, okay, so we have fixed the concentration of the enzyme, and now we have to fix the other variables. Regarding the oxidation reaction, the only variables are the alcohol concentration and peroxide concentration. We use the software to predict these values, and these are the values for the initial concentrations. And regarding the aldol addition reaction, the concentration of the aldehyde comes from the first reaction, so the variable is only the concentration of the DHA. So we do these reactions using soluble enzymes, and when doing the oxidation reaction, we saw that the model fitted the data properly with a similar yield of the aldehyde, but when doing the aldol addition, the model did not fit the data because somehow the FSA was inactivated in the system even when doing ultrafiltration between the first step and the second step. So the prifagomine yield was 40%, whereas the predicted value was 80%. If we do now the two-step synthesis using the enzyme immobilized magnetic nanoparticle clusters, the oxidation results were similar to the soluble ones, and however, the aldol additions, we observed a lower yield of prifagomine than when using a soluble enzyme. And this was because the enzyme was inactivated faster than before. So we can finally say that the enzyme immobilizing magnetic nanoparticles cannot be used in this reaction. But when doing the two-step synthesis using the enzyme immobilizing agarose, we observe again similar results in the oxidation. But surprisingly, we observed that the yield of prifagomine was higher here than with the soluble. And this was because the enzyme was more stable. So we managed to stabilize the enzyme and then to increase the yield to 96% of prifagomine in the second reaction. So finally we get near 20% of prifagomine yield on the overall reaction. This reaction using the enzyme immobilizing agarose was also performed in one-pot configuration, but no prifagomine yield was obtained. So we have done the exploitation of the model and to find the optimal conditions of the operation in one-pot synthesis or in two-step synthesis. And the best results were obtained in the two consecutive cascade reactions when using the enzyme immobilized on agarose with an overall yield near 20%. And it were to say that a further study of the immobilized biocatalyst on agarose would enable the correction of the model parameters to find the optimal values, because this model has been obtained using the soluble form of the enzyme. And finally, the general conclusions of the thesis were: the oxidation capacity of CPO of amino alcohols has been studied regarding substrate structure, and also confirming the acceptance of beta-amino alcohols as substrates. We have identified the bottlenecks in the coupled reaction, but we observed no yield of prifagomine, and we also identified some side reactions. And then two solutions were proposed: a mathematical model that has been developed, validated, and also the mobilizations of both enzymes to increase their stability. And these are the four selected derivatives. Finally, the model has been used for process intensification in order to determine the optimal operating conditions for the coupling. We have used the soluble and these immobilized derivatives in the reaction, doing the reaction in one-pot synthesis or two-step reactions. And finally, we got a prifagomine yield near 20%. And finally, I'd just like to thank my group and all the people from the department.
Thank you. So now we will start with the questions, and the first person to ask questions will be
Thank you, Marielle. Thank you, Gerard, for the presentation. I would like to make the presentation before to read the thesis in order to an overview of it, because I'm not an expert in concrete in these reactions, and well, sometimes I need to get one page for the reactions, one page for the kinetics, one page for the nomenclature to try to understand all the. That is my problem. It's not the problem of the people. I also would like to thank all the directors of your thesis to participate in this jury, and to understand a little bit more of the conversation that we had in the last 4 years in the coffee break in the morning about the problems of yours and science. Okay? Before to make some questions, I also said some advertisements about the structure of the PhD thesis or the document. For instance, in page 33, in table 3.1, for people that forgot the organic chemistry many years ago, perhaps I would like to see the list of the amino alcohols with the structures and not only with the substitutions. It's a visual effect more than this one. And thank you. Okay. And similar about the table 3.2 with the amino alcohols oxidation. And other questions about chapter 3. I'll try to get an order of the chapters. In page 43, you say that the peroxide addition rate was fixed at 3 millimolar hours minor 1. Why this constant rate was selected and not other or not an exponential rate?
Because all the results in the published paper from Enzymtic, they tries different oxidation peroxide additions rate, and they use this 3 millimolar.
Because it's not possible to the monitoring of the peroxide into the reaction. It's complicated.
Yeah, we monitorize the peroxide, but after the reaction. So we wanted to study this addition, and it was a variable to study. But finally, after doing all this model, with using the model, we saw that the peroxide has to be added the high concentration in order to get enough aldehyde for the couple reaction. Because when doing these simulations, I try to write this continuous addition and see if I can get the estimated value of this addition. But the model always wanted to have a high concentration of the peroxide.
Because an exponential or a step addition perhaps could improve the stability of the enzyme.
Yeah, and it was also because at the beginning we used this addition in order to maintain the peroxide at a low level to reduce this concentration, to this inactivation of the enzyme. But we always thought about, we will study later about when copying.
Other question is about the mass balance in page 45. When you discover that there are some no desired reaction. In the page 45, you say that you have 4.15 milligrams missing of the mass balances and balances, but this 4.15, what percentage of the mass balance is around? The mass balance is it's okay in 90% or?
No, yeah, I think it was maybe 20% or of the substrate or product were missing. But it depended always on the peroxide and also depending on the peroxide that you have used. And so it was not always the same, but it was nearly 20%, I remember, more or less.
The question is, you expect other not identified reaction, or perhaps it's a typical error of the mass balance?
No, because we did many reactions and we observed this imbalance. So we thought, okay, maybe it's experimental error, but when you get this always, and it was always similar, or quite similar. So we thought, okay, maybe we can try to see if there's something else happening in the reaction. So we had this substrate and product. We have the alcohol, aldehyde, and amino acid, and we did incubation with peroxide to check this effect. And when doing this incubation, we saw that the aldehyde concentration was lowering during time when incubating with the peroxide. So with this, we thought, okay, there's happening a chemical reaction or something inside. So we did this. We did validation with MS analysis and animal.
Okay. About chapter 4. The FSA is produced by microorganisms. The fermentation was made for you, and the purification was made for you, and it's not clear in the document, or a little bit clear. And I think it's important for the formation that it's a multidisciplinary work, but there are more multidisciplinary work than spending here. And at this point also, I recommended to put at least in the introduction a brief explanation about two pages about how this enzyme is produced, because it's not a conventional enzyme that you can buy in Sigma or in other. And about the pH selection, in page 56, you select a 6.5 for CPO, but if you see the table 421, pH 6, the activity retained is 50% more or less. When you page 56, table 4.2, when you have all the enzymes and the oxidant. Okay, the first. At 6 is 50 and at 7 is 10, more or less, no? And you select 6.5, but 6.5 is near to 50% or near to the 10%?
We didn't check this activity as in this because first of all we did the pH stability of the enzyme, but only the enzyme in the buffer, which is shown in the previous page in the figure 4.1 in the graph. And
Yes.
we did this study, and we saw that at pH 6.5 the activity of the CPO was near 100%, or I mean, no meaningful inactivation was observed. But when doing this compatibility of the enzyme, we only perform the incubation at pH 5, 6, and 7. But so here it was only to determine that there was some inactivation of FSA with the incubation of CPO and peroxide. But the problem was that we observed precipitation of the FSA at pH 6, but not at pH 6.5. So we choose pH 6.5, and we thought because according to figure 4.1. The CPO we know that was stable with the buffer.
No, I understand that you need a compromise between the two enzymes and the oxidant to try to get the reaction. Okay, about chapter 5, well, it's a surprise for me because I think it's the first time that in the department we convince a biotechnology profile student to cross the frontier from the omics to the cavern of classical chemical engineering, no? And I think it's curious, no? Very curious. And the result of the kinetic is quite good. Not? I enjoy with the chapter, but have some doubts. One is in page 6 is in general when you make all the experiments, individual experiments to get the kinetics of the constants kinetics, you always start with a selection of experiments. And I'm not an enthusiastic of experimental design, but when I see the selection, perhaps the first impression is that it's aleatory, this selection. Why not an experimental and rational design of this data?
At the beginning, for example, let's show an example.
In page 72 is the one.
Yeah, we tried always to do vary concentrations of the variables, but always having some values that we can measure. And it was, I mean, there's always, if I put a lot of peroxide and low concentration of the enzyme, the inactivation is too fast for me to measure. So it was always to find some values to get a range that I can measure properly with different samples. And also I wanted to say that, for example, in page 85, this experimental distribution, like this, because at the beginning we tried to do initial reaction rate analysis. So we fixed one concentration of one substrate and we varied the other substrate concentration. But when analyzing all the results together, it was very complicated to develop a model only with initial rate analysis. And of course, if I have to do it again, this wouldn't be the experimental distribution. I'll try to get all the range, but also points in high concentration of both variables and so on.
Okay. Another question is about the results obtained from the parameters. For instance, in table 5.1 in page 75, the 5 parameters that you have here are values. There are some restrictions in the values of these parameters, or it's completely free and it's the program that decided what is these values. The question is, if it's yes, the answer is yes, could be another set of parameters that describe also quite well in the model.
It's very difficult. I mean, of course, I think you can find another solution, because when you use the model software, you enter all these values that you have, and then you have to assign experimental error to the model, to all the data you have. But sometimes some experiments can be ponderated
Yes.
different, because according to this, maybe the experimental distribution today it's not perfect.
There are weights in the model. You can put weights of.
Yeah, you can change it.
Okay.
So you try to maybe put more weight on the range, on the sides.
In fact, you can concentrate the wrong or the uncertainty in one of these parameters.
Yeah.
Okay. And it will be tested or compared with some values obtained in the literature. And if quite similar in the magnitude order, something like that.
We didn't check at all, but with the literature, because we didn't find other of this.
Okay. Other question is about the exploitation of the model. Part of the exploitation of the model is made in soluble enzyme, but other part is in immobilized enzyme.
In fact, we always do the exploitation with soluble enzymes, because the model has been developed using soluble enzymes. But we know that the optimal conditions for a soluble enzyme reactor is not the same for immobilized, because for instance the activation is different. So then
so you have to change.
Yeah, you have to study also with immobilized.
Yes.
So we only wanted to optimize to find the optimal conditions for the soluble and try if the immobilized enzyme can give better results in terms of yield. Of course, this is not the optimal values, and that's one of the conclusions of chapter 5, that if you do a further study with the immobilized derivative on agarose that show better results, you can correct some of the kinetic parameters, such as inactivation of the enzyme, and also there are some diffusion limitations, so you should correct all these values and equations, and then maybe you can find better initial conditions. And
no, because if I have to make a critical of the model, is from the chemical engineering point of view is excellent, but from the practical point of view, perhaps it's a model that never to use, because probably you use in the industrial reaction immobilized enzyme. No? And the question is, what is the apport of the model in the knowledge of the general knowledge of the two reactions, the real apport?
For me, it's not only that you have a model that can predict all the data, but also it's like a way to understand of the mechanism in the reaction. Because at the beginning we thought, okay, we can maybe do a factorial design to get the optimal initial conditions. But if you do this in this reaction, maybe you're lucky you can get a point. And with the initial conditions to the reaction, but in fact I think that you don't understand the mechanism. And by doing this, we develop a model for the CPO and also for the FSA, and then everything together. And yeah, it's true that if you want to use the immobilized enzymes, you cannot probably use it, and you have to correct it, but we have shown some potential way to improve reaction. Maybe you have another system. Of course, it won't be the same, but it's a methodology trying to separate all the reactions and further step addition of other reactions.
Change of the chapter of immobilization or the new methodologies of immobilization, because it's not a conventional immobilization, both in agarose and in nanoparticles. And my question is about the stability of the colloidal agarose. It was made, the stability, in page 166. Oh, sorry. 165.
167, maybe?
See, when you are working with the immobilization of CPO, I don't identify in the text if there are some study of the stability of these preparatives.
No, because I think it's
because with the FSAs, there are a typical table of different cycles and the loss of activity. But in the CPO, I don't identify in the text.
in CPO,
Yes.
In CPO on ours?
In the CPO,
Sorry, I'm not sure about your question.
there are no data of stability of this immobilizer, of the best immobilizer proof
Of CPO?
of CPO.
But you mean reaction cycles?
Yes.
Or, no, because the in the case of FSA, the enzyme, we expected that the enzyme is not inactivated in the reaction, so we can perform reaction cycles, although at the end there was some kind of inactivation. But in the case of CPO, the reaction was stopped when the enzyme was inactivated. So there was no possibility of doing reaction cycles. Of course, we can do reaction cycles with other reaction concentrations. For example, if you use a low concentration of the peroxide, the enzyme will be stable, but for us there was not the point of doing this. We showed that the enzyme was shown higher stability, but for our case, we were not able to convert all the alcohol because the enzyme wasn't activated. So.
My final question is about a practical advice for the next student, PhD student. In what part of the process you intensify the study to get a little bit higher final yield of the complete reaction?
For me, the key point here is the inactivation of the FSA, because of course the CPO gets inactivated, and trying to find maybe other additions of the peroxide or using modified CPOs with better stability to peroxide could enhance the process. But for me, the problem is the inactivation of the FSA, because when always that we did a couple reaction, CPO wasn't activated, but not at all at the end of the reaction. But the FSA was fast inactivated just when starting the reaction. So, for example, doing some genetic modification of the enzyme could enhance this, but you have, of course, to understand what is happening, because if you don't understand what is exactly the inactivation of the enzyme, you cannot do just a mutation, random mutation, and see what happens. So.
Okay. Thank you, Gerard.
Okay, thank you, Paco. So now Carmen will ask you some questions.
Thank you. first, I would like to express my gratitude to the directors of the thesis, Professors Josep Lopez and Gregorio Alvaro, for this invitation to participate in this defense. It's always a pleasure to be here. And also I want to congratulate them, and especially you, Gerard, for the high quality of this research, of the manuscript, and also the presentation. I think that the manuscript is very well formatted. It looks very professional. The work is perfectly contextualized in the introduction of in the chapter of introduction, and I think that it implies a lot of work. Not only work concerning analytical methods for identification, quantification of compounds and different mechanisms. Also, you have improved analytical methods for quantification of enzymatic activity. Also, you have used NMR and so on, and you have elaborated over a complex kinetic model that fits your data. So I think that the work is high. So let's go step by step. First, I would like to know what was your criteria to consider the beta amino alcohol as the best compound to obtain immunocyclitols? I mean, in the first chapter, you have screened some amino alcohols for the oxidation to aminoaldehydes and then amino acids or whatever, and you have observed. So you selected alpha, beta, gamma, etc. And you have observed your results say that alpha amino alcohol, which is ethanolamine, I think, has better yield for the production of the final compound than beta amino alcohol. So beta amino alcohols are very used for the synthesis of beta amino acids because they are known to be bioactive compounds and they have interest, but I don't know, or as far as I know, there is no reason to use a beta amino alcohol or a special reason to use a beta amino alcohol for the synthesis of immunocyclitols. Could you explain?
It was just because the project was to synthesize immunocyclitol, but in particular the D-fructose. And in order to get this D-fructose, we required to do the oxidation of the beta alcohol. And of course, after this table, after doing this substrate specificity, it was like, okay, maybe beta amino alcohols are not the best for this enzyme, but we wanted to check if we could synthesize this D-fructose by using the CPO and the FSA couple reaction. Of course, after seeing this, it was not the best results. When you do this substrate specificity, you saw that the beta alcohol, the initial reaction rate is lower and so on. But it was the product and it was the project that we wanted to study. We decided, okay, to do this oxidation and let's check if we can increase the yields.
In the same chapter, when you compare the substrates, the specificity of the enzyme for the substrates, you compare the results using two different substrate concentrations because due to solubility limitations, 5 millimolar and 0.5 millimolar, and then you compare the initial reaction rate of its reaction. So, as you are using different initial substrate concentrations, you use a normalized initial reaction rate. I suppose that you are considering that the reaction rate is a first order kinetics or has a first order kinetics, so you are dividing, I suppose, initial reaction rate by initial substrate concentration.
Yeah.
So there is something that's units. Units, I think, should be time raised to the power of -1, isn't it? And you obtain normalized initial reaction rates in micromole per hour. I don't know if it is just a mistake or the normalized initial reaction rates are calculated by other way. It's page 37?
Yeah, 37. I think I agree that if doing this, you divide this value on the concentration, of course, they're not the units, but I think in this case, what we did is take into account the concentration of the initial concentration of the substrate. So what we did is to multiply by 10 the concentration that were lower. So these are the units. We should.
The real units should be.
Multiply them.
Okay. Okay, and going to the model, I'm very curious to know which was the process that you followed to obtain these final results. I mean, you have presented here the final equations, the final mathematical model, but I suppose that you didn't.
Came out with this.
Yeah, the process was longer than the thing that we can see here. No?
Yeah.
I suppose you obtained or you decided different mathematical models. I don't know, maybe using bibliography or just knowing the mechanism of the reactions, or what was the process?
It was difficult. We tried always to, for example, the CPO oxidation is described in the literature with the ping pong mechanism.
Mm-hmm.
So we use this ping pong equation for as the base of the equation in the oxidation of the CPO. But for example, let's go with the equations. But sometimes it was difficult. For example, in the case of the degradation of the peroxide, which is on page. The equation is the final equation, page 72. This equation, it's not a ping pong mechanism because, for example, here we saw in the literature that this reaction has been described, this degradation of the peroxide, and that I think you have in the previous page, you can find the stoichiometry of the reaction, R4. The 3 moles of this hydrogen, the butyl hydroperoxide, is converted in 1 of the butyl pole and 2 of this radical. So by using this stoichiometry and checking all the results, we observed that it's not a typical reaction of one substrate, one product, because it is 3 reactions on it, because in the literature it's you have the enzyme, and then when the butyl hydroperoxide comes into the active site, activates the enzyme, then another molecule of the butyl hydroperoxide comes in, and so it's a 3-step reaction. So it was difficult to express this as a kinetic equation, also because we cannot follow the products, because one is a radical and the other butyl pole we couldn't measure. So we tried to do it in just one equation, like if it was just one reaction. And after doing some experiments and also doing some data that it's not shown here, that initial reaction rate analysis of many reactions, we saw some sigmoidal behavior. And that's why we decided to use this reaction with this equation, and with this equation, all the data, or almost the data, was fitted by the model. So it was always trying new equation forms and check if it was okay or not, and try again and again. And for example, in the chemical reaction, we saw it was a kind of equilibrium. So we said, okay, we will add two reactions. It was always difficult to decide what equation to use, but after doing tries and tries, we managed to find at least an equation that maybe it's not the best correct equation, but it describes the data. So this was this problem. So it's trying to fit the data and adding some terms, but not a lot of terms, because then the model will not predict the data. So yeah.
So time consuming and some disappointments. Okay. Have you obtained some correlation coefficients or something like that to know which is the best fitting or the goodness of the model?
I haven't checked it for this. I mean,
because it could be interesting to know
yeah, every time that you predict the data with the model, with the simulations, when estimating these parameters, the model gives you an error. And I guess it's this, but I try always to minimize this error, but it's a number that for me it's not like something that I can, but I guess that it's a way to see if the data, it's not just arbitrarily.
Okay. So I like this part because I think that it implies a lot of work, but I miss some more discussion or conclusions from the model. I think it should be more exploited. For example, you have obtained Michaelis-Menten constants for CPO, considering terbutin hydroperoxide, which is 58 millimolar, aldehyde, which is 36 millimolar, and alcohol, which is 300 millimolar. Do you think that this data can be compared, so we can obtain some conclusions from them, or because it's a part that you have not discussed a lot? I mean, you have some values, but maybe we can obtain information from them.
Yeah, of course you can compare the values and all these KMs, because they correspond to the affinity of the enzyme. Yeah, of course you can do this, and it was not done.
So because I think it's quite important that with aldehyde 36 and for alcohol it's 300. It's much more affinity for aldehyde than for alcohol. And maybe we can. It could be useful for some to take some decisions for the performance of the reactions. So, as I said, I think that the main purpose of the model should or can be maybe to optimize the process in order to obtain the highest production of pharmamine, but also maybe, and this is a part that you developed in the last chapters, no? But also you can obtain more information. Maybe I think that there is a correspondence between, or a relationship between the initial concentrations of substrates, at least for CPO. I mean, in some experiments you have obtained, or you have used continuous addition of peroxide. At the end of after the development of the kinetic model, in the validation chapter, you apply the concentrations that the model gives as the best ones for the development of the reactions. But when you cannot use these concentrations because the enzymes, when you use the immobilized enzymes, you cannot use the concentrations that they provide, that the model provides. And you use other concentrations, considering, for example, that the relationship between peroxide and substrate should be maintained. Do you follow me, or?
Not at all. I mean,
I guess, but
So I can do it better.
No, I mean, I think you get the point, but you mean, okay, I'm fixing the enzyme concentration, and then I have these two variables, the alcohol.
No, at the beginning you are using a fixed concentration of peroxide, addition of peroxide. But at the end of the work, you are considering that the peroxide should be should maintain a ratio, a fixed ratio with a concentration of substrate.
No. I mean,
maybe I didn't explain myself. What we did in the exploitation, it was to use the model to get the optimal values of the peroxide and the alcohol, but there was no ratio, limited ratio.
Yeah, but then when you use, you use soluble enzymes, and then you repeat, or you try to repeat the process, the reactions with immobilized enzymes.
Yeah.
But you cannot consider the same values given by the model because you don't have enough enzymatic activity or enzymatic concentration, isn't it? So I think I think that it's in this moment when you decide to maintain the concentration of substrate, the ratio substrate peroxide constant.
No, because I mean,
I try again. Can we do it, please?
No, I don't mind. It's just to say that concentration of peroxide maybe should be in accordance with the concentration of substrate, because if you use a high concentration of peroxide, maybe you can inactivate the enzyme. If you don't have a high concentration of peroxide, considering the concentration of substrate, you have not enough to develop the reaction. And also there is an effect with the CPO. So there is in page 92, you have two experiments. One of them, the two ones are considering the same concentration, initial concentration of amino alcohol and the same concentration of terbutyl hydroperoxide. But the difference between them are that the first one uses 0.4 milligrams per milliliter of CPO, and the second one uses 4 milligrams per milliliter. So the difference is that in the second case, one of the differences is that in the second case, you have a total loss of peroxide concentration in 20 minutes. So maybe this is okay. I want to see that from here you can say that the concentration of substrate, peroxide, and CPO maybe should be more or less balanced. So this is some information that I think that you can take from the model. Apart from the optimization of the production phargomine, you can obtain more information to perform reactions if you are not able to work always in the best conditions. I think that this is some part of the work that can be more exploited. Concerning immobilization, I have no clear why you use magnetic nanoparticles in a cluster. I mean, you say or you assess that there is a larger surface area using clusters, and also that if you use nanoparticles themselves, you need a high magnetic field. But on the other side, if you use nanoparticles themselves, you have more ratio surface volume, which helps to save costs, which is very important when using supports for immobilization, and also you avoid agglomeration problems. So I don't know if really a high magnetic field is so important unless this can cause some inactivation of enzyme or something like that.
For us, it was to have, if you have just a single nanoparticle, of course you have Huygens surface, but the problem was this, in order to do the reaction and get the enzyme, you need a very strong magnetic field because it was these clusters, okay, you are losing this surface volume advantage that you have with the nanoparticle, but they do not agglomerate. Because of this, we have this behavior of supermagnetism nanoparticles. And also it was very easy with a small magnet to get all the nanoparticles. And for example, at the beginning we thought, at the end we didn't do this, but to do a reactor configuration using a magnetic separator. And by using this cluster with higher volume, it was easy to just very fast to get all the nanoparticles in a continuous flow. It was done with this collaboration of this group, and they work a lot with these materials, and they show this separation. So yeah, you're always losing something instead of, but so in this case we decided to.
But you had some problems of agglomeration, isn't it?
We had, but it was after addition. For example, I think you can see when we did the characterization in the ionic case there was no agglomeration, but when doing, I think it's 163. But when doing, when adding covalent agents, like for example caporimide, then of course we had some agglomeration because nanoparticles can themselves and agglomerate. But they also tried this group to do some addition of PEG groups in order to reduce this agglomeration, these polyethylene glycol groups, because they are a large chain of carbons, and then this agglomeration between particles was reduced. But however, some of them was observed.
When performing in the last chapter, when you validate the model, you perform reactions in one-step or in two-step systems. And in two-step system, I think that you are maintaining pH at 6.5. Do you think, as the stability of the enzymes is very dependent on the pH, do you think that you could use the two different reactions at different pHs?
Yeah, we thought about
it seems to be easy.
Yeah, but then the aim of doing maintaining the pH, that we can use the model to predict the data because the model is at pH 6.5.
Yeah,
but also it is easier to just like you can do a continuous flow using like two membrane reactors. And if this was, if the yield of these reactions was higher, you can work with this continuous flow. But however, the yield was not high, so maybe trying to use two different buffers could be an improvement on the system. Sure.
Maybe you're not using. Okay, you're not exploiting the model, but you are obtaining a higher value. And just to finish, some more general question. You are now an expert in enzymatic modeling. Do you think that, or do you feel you are able to integrate hydrodynamics in order to obtain a complex model, a complete model, where you can foresee what happens when you add peroxide in continuous mode, or enzymes or DHA in a continuous mode.
Yeah. I could try, and also we tried with using the model and trying to add this semi-continuous addition of the peroxide in the model by adding some equations and so on. But as the model predicted that this reaction was not a beneficial step, we didn't exploit this. But of course, I mean, after doing this, I get some knowledge of kinetic equation, because at the beginning I had almost no idea of kinetic or enzyme kinetics, just some theory. And of course, it would be great to add some steps, some additional, not in this, maybe not in this reaction, because I'm not sure if it could improve a bit the yield, but yeah, but of course, in another reaction it would be.
Okay. That's all. Thank you. Congratulations. Yeah. Thank you.
Okay, thank you. So I'm the last one. Like my colleagues, I would like to first thank Josep and Gregorio to invite me here. It's my first time here in Barcelona, and I'm glad to be here and to hear you, and also read your thesis. It was very interesting, and I also join my congratulations that you really did a very good job with a very nice presentation. I have also questions, and I will start with the first general question with the scheme you have in page 3, because you said what difference you have written specificity and selectivity. So which difference do you make on this? What do you mean exactly?
I mean, when you have you want to synthesize a product, you think about substrate and maybe the possible reaction. So you need an enzyme to catalyze this reaction, and it's important to check if this enzyme is able to accept this as a substrate, check the specificity of the substrate specificity, and also to check the selectivity of the reaction that catalyzes, because sometimes the reaction can be performed, but it's not enough to cure, and you can get some other products, and then you have to add, of course.
So you mean substrate specificity? Yeah. Then, well, I know that well, in France we are used to write a manuscript that can be then corrected. So I think it's not the case here. It's the definitive production. However, you have a mistake, page 13, in the scheme 19. Which mistake?
Yeah, I saw that in the presentation that at step 1 it's not required, because you don't have to remove phosphate.
But it is in the context of DHAP aldolase.
Yes.
So
Yeah.
something is missing. Is the phosphate?
Yeah, the phosphate. Sure.
So then, for the CPO mechanism, you have presented page 20, the mechanism proposed from the literature. But in which way your aldehyde is produced? I mean, you have an alcohol, so in which, because you have AH, you have different reactions, and this scheme is not reflecting the oxidation of alcohol. So how would you introduce? Which way will you choose?
The first you have the enzyme and the peroxide enter the active site, and then you have compound 1.
Yes.
That is a CPO active CPO, and then the aldehyde comes in the active site.
The alcohol.
And yeah, you have the
No,
alcohol.
but I mean to get the aldehyde, the alcohol.
The alcohol gets in, and then you have that the aldehyde can be released. But first,
in which because you have presented the reaction mechanism in your scheme 115.
Yeah.
And which way will follow the alcohol on top?
I think it will be.
So you will prepare a radical from the alcohol?
I'm not sure, because in the literature I found the mechanism of the CPO is not studied in the oxidation. I only found one. It was from Casella, and I think it's not this one, on the oxidation of phenols, and they write some kind of radicals, like in this case, like when the alcohol interacts with the enzyme, some kind of radical is formed, because it's like 2 electron. Yeah, but I wasn't sure about that, because there's not many.
Nothing in the literature. Okay. Then I will ask question about the substrate specificity study, and I also have comments on your table, page 37, because in this table, so you have tested several alcohol, and what do you? I mean, it's I don't know if it's in English word implicit. I don't know. It's something that is inside. Implicit, you will wait for the aldehyde, right?
Yeah.
What do you expect? The aldehyde?
Yeah.
In all cases?
Not in all cases. I think because the structure is not.
Oh, the ketone.
Yeah.
The ketone for 2C.
It's 2C.
Okay.
Yeah.
So what I mean is, when you read then a little bit further, then you discover that the aldehyde can go on chemical reactions.
Okay.
And also the aldehyde can be transformed into acids, right? So what do you think that this initial rate would represent? That you have calculated.
Yeah, I calculate this analyzing the alcohol concentration. But of course, if you have other side reactions after this aldehyde synthesis, it can somehow interfere in this, because if you're forming the product and the product is released to another reaction, maybe these results are not that correct and showing that.
And the conversions, and when you read it, it's not very high for 2A, but 2B or 2C, but 2B. 2B is the same amino alcohol with no protection, right?
Yeah.
So 44% conversion, you will say, oh wow, it's a good one. But what could happen with this amino alcohol?
If it's not protected.
Because the conversion is higher than your model alcohol.
Yeah, but if you don't have this amino protecting group, once you are getting the aldehyde, you can get undesired reaction between the amines
Have you tried amino compounds, just amino compounds with this enzyme?
No.
Or is it described in literature? What could happen with amine and
I think it can be oxidized as well. And I know.
That's why I don't like very much this table because I know it's published, but
you will have other reactions inside there.
yes, it doesn't reflect substrate specificity as you could imagine it for an aldehyde, because you are looking for aldehyde, and it's the objective of your thesis. So and well, a comment on that you introduced the lower initial rate with compound 2C, which is giving you a ketone, and you said it's hindrance because of the methyl group. But as a chemist, I would attribute that to a different reactivity between primary alcohols and secondary alcohols. Okay? Because it's, well, probably, or okay, maybe it's due to steric hindrance, but
maybe it's more the reactivity of the alcohol.
Maybe. Then well, the figure 3.6. I have a question concerning because you said you have other reaction. So what kind of reaction is it from the aldehyde to the compound 6?
The aldehyde to compound 6.
Okay. What did it look like?
It's a chemical reaction between the aldehyde and the peroxide. So
the closest compound you could compare with compound 6.
The closest compound, it's like a peroxide, I mean, or
and if you are not considering the peroxide,
you have you have the alcohol, you mean, or because you can
what kind of a reaction is it? I don't know what you studied before, but
biotechnology.
Sorry?
Biotechnology.
Okay, so not that much on organic chemistry.
Not really.
I see that. Well, it is an addition reaction. Okay. I want to make the point on that because this is, in general, pH dependent. This type of reactions. It's easier when you change the pH and mainly in acidic conditions. So did you explore?
So in acid conditions?
Acidic conditions, this could be easier.
To avoid it?
No.
Okay.
No.
Yeah, but if...
So you are at pH 5?
Yeah, but if we increase the pH, the CPO is not really stable. Finally, we studied till 6. So.
But did you explore that this reaction at different pH or no?
Not separately. So we tried this reaction later in 6.5, but we didn't compare like.
Okay, because at pH 6.5 could be less.
It could be
less
less.
than
Maybe we could explain that. I think that in reaction 6.5, the balance was very close. There was not that imbalance, so maybe this reaction was reduced.
That's why it's important to know that, because I think, I mean, this is close to the addition of alcohols, and it's like any kettle, and any kettle are easier prepared in acidic conditions. So increasing the pH could have limited this formation. So now I will probably ask more detailed questions on FSA. So at page 51, you present the activity assay for FSA. But I am missing one thing: is did you use a buffer, and what pH did you do that?
We didn't use a buffer because the activity assay that the protocol that we get, it was this one, but we check and the pH was always near 8.0, I think, because of the imidazole. But
when did you use imidazole?
Because we didn't develop this activity assay. We just get the protocol because they were using this.
Okay.
And we measured activity always with the same test, and we checked activity and the pH many times, and it was always near this 8.0, I think.
So near 8. Okay.
8 or 8.5, I'm not sure now. But
8 or 8.5?
Yeah, it was 8.
So then you said that with this measurement you got 15 units per milligram of enzyme, right? This is what, which is quite high. And why not? But we never got these higher values in our lab. I don't know in Perez's lab, but well, why not? And then, how do you purify it? Because in you said it's described page 211 and 11. But when I read it, I couldn't understand how you did it.
We do it using this corrida agarose, and we did this in batch.
In batch, and then? Because, yes, you said the final disrupted volume was incubated with 15 grams of co-ida and left under mild stirring for 60 minutes. And then what do you do?
Then we just filtrate and just to get the agarose with the enzyme.
Okay, and then?
And then we add some buffer.
Okay.
And with high concentration of imidazole in order to elute.
If you read it, there are missing steps. Okay. Because then you said that then 300 millimolar imidazole was added and left for incubation for 60 minutes.
Yeah,
so that cannot work like that way. To elute the protein to the supernatant, finally purified FSI was recovered by filtration. So it's not possible to do it. Your protocol, so it's published now, but you should correct that because it cannot work like that. Okay. So when you did your different assay with FSA, how did you do it technically? I mean, you are trying a reaction, for example, changing the different buffer. You tried pH 5, pH 6, pH by changing the composition of the by changing the composition of the buffers, right? For example, you I mean, when you do your reaction and you want to combine them for the first preliminary coupling. Okay, so how do you do it? For example, to obtain this figure 4.1 at page 55, technically, how you do your experiment?
So which figure?
55, figure 4.1.
Okay, yeah, this figure was obtained during the activity assays. So
what do you do? So you start a reaction.
Yeah, it was not a reaction. It was just the enzyme in buffer. So we take several samples of this enzyme, dilute it in the buffer, and we analyze in a parallel activity assay.
So you take 15 microliters of this mixture, and you add it on a cuvette, okay? And your cuvette is at pH 8.5, right? Am I right or no?
Yeah.
So how could you measure the activity of the enzyme if you change the pH?
Yeah, okay, I get the point, but we assume that if the enzyme is inactivated, it will not show activity. So if you do always the same, I mean, you start this incubation at pH, let's imagine pH 6.5, and you take sample and you do the activity assay at pH 8, and you measure the activity, and you will get the one value. But if the enzyme is inactivated, and later when you change, even if changing the pH, the activity will be lower. Of course, the pH can help change the configuration maybe.
But the problem I will not work like that because what we had with experience, the FSA cannot work very well under pH 7. Of course, it is described in the literature that the pH is range from 5 to 11, but at 5 it's almost no activity. If you imagine, and you said yourself, it is written in your manuscript that you observed precipitation. So if we imagine that you take the sample and you put it, and you could have a reverse effect. So you could have we don't know. I'm sure if you want to measure the activity of the FSA at pH 5, you will find almost no activity. So I think if you want to measure the activity of your enzyme, you have to measure it in the same dosha, in the same. You have to change, so your activity test must be done in the same pH. Otherwise, it doesn't reflect the real conditions, because you could take a soluble part that is still active, and you measure an activity. And as you compare from the beginning, you do the same things at the starting point, and then you leave it reacting, or you understand?
Yeah, of course. I mean, but
and I think this is something important for all the discussion and the problems you observe, and my colleagues ask you some questions on that. Because you observe also inactivation of FSA quite quickly at pH 6.5, but I'm not surprised by that because it's not a good pH for this enzyme.
Yeah, but we try to do it.
So I'm sure if you do it, you only putting this enzyme at pH 6.5, you will observe probably the same curve.
But when we studied the reactions of in order to get the kinetic parameters of the aldolation with aldolation, the reactions are performed at pH 6.5, and we got the prefilmine yield. So we know we assume that the enzyme is inactivated because without the CPO and the peroxide, the FSA can catalyze the reaction, even at pH 6.5.
But did you observe by time? You do it, you examine that leaving several hours?
Yeah, we have
so no deactivation?
I think.
But I'm sure that this specific activity that you are describing, 15 units, is not 15 units at pH 6.5, because you are two 2 units of pH lower, and the activity cannot be 15 units. Okay. That's not possible. This is okay. Then I have questions. Oh, if I, well, no, I will not go back to that. Oh, yes, it's the model that you, so it's for part 5. The model that you said you have taken it for FSA, it's BB, an order, right? Sequential model, and you said it looked like 1 in your figure 5.4.
65.
Page 65, right? Yes, sorry.
Yeah.
And you said that FSI is like model 1, right?
Yeah.
But I see A and B giving P and Q. So what will be Q in aldolase reaction?
Yeah. Okay. In this case, it's not PP. It will be like.
And another thing is that so I don't know in your model how far this can be. So you said it's also irreversible, but what is the principle of an aldolase?
Sorry?
The reaction, you mean it's an irreversible BB, is two substrate reaction considered. Two substrate A and B giving two products P and Q.
Yeah.
So there is no Q for the aldolase. And then, is it irreversible?
No, because we know that for
Yes.
FSA it's
So how did you adapt it, your model then? Because it's not no other model were existing that you could.
I found another model, and they use a random sequential mechanism for like because in random sequential it's like two substrate charismatic kinetics. But I wanted to use this equation for the order sequential, even if it's not BB substrate mechanism, because I tried and the model was able to predict the data with this equation and all the tested conditions. So of course it can not be maybe the best equation, but always it's you have to try a new equation that predicts your model and your data, and it does. And okay, for sure, it is not the correct mechanism, so maybe there's another equation that is able to predict properly the data, or maybe in another variable range.
So well, I saw that you introduced this R7 in your model, the return reaction R7.
Yeah.
Yes. But
yeah, of course. You say that it's
so
it's
you knew that it was reversible and not irreversible, but
yeah.
I was just wondering how this could be.
Yeah, but we consider for the aldo addition, like, okay, it's irreversible, but the enzyme can do the other way. But for this equation, it's always like do an approximation, and this is the equation that we decide because it was okay with the data, and it was similar to the equation that is publicated. And the publicated is random or sequential, and we didn't agree that it is random because, of course, the DHA goes first, and so we try to use this order sequential, even if it's not
Okay.
correct.
Yes, in the immobilization part, I have noted the slide. It was in slide 62, but you said that there is no covalent attachment with the alkene. And how did you determine this how did you determine that it was covalently attached or not?
By incubation of the derivative with sodium chloride, increase the ionic strength, and if the enzyme is released, then the binding between the enzyme and the support is not covalent. And after doing this incubation, we observed that the enzyme was released to supernatant. And in this case, at the beginning, we thought that the binding was through the alkyl group. But when synthesizing another cluster with another type of alkyl molecule, we observed that the binding was not through the alkyl group, but through hydrogen bonds of this molecule, or so-called electrostatic binding.
Okay, because if I remember, I don't which page it was in your thesis, but I think you had quite a good retaining activity and high yield of immobilization. So.
Yeah, you were right, but as we require covalent binding because in reaction conditions the enzyme was released, finally we chose another derivative.
And what do you think? It's more general question, but would you continue to chemically modify, for example, FSA to try to covalently immobilize it, or?
Yeah, because we've seen that with, for example, with the agarose, after the immobilization of the enzyme on agarose, the enzyme is more stable to this inactivation of the peroxide and the CPO. So maybe with another derivative in magnetic nanoparticles also as well, we can improve this stability. In this case, results show that the derivative on magnetic nanoparticles, the one that we selected with FSA, was less stable than the soluble enzyme. But of course, you can try other immobilization and get better results. We tried to do a similar immobilization in clusters as in agarose, because in agarose we immobilize through the heat stack, and we tried to do this in using the clusters, but we wanted to synthesize this cluster with aminodiacetic acid on the surface, but the preparation was not successful. So maybe with these particles or trying with another immobilization, you can improve this stability. And
okay, so why not? Because as you said, this enzyme is quite rapidly inactivated. So I was wondering if it would be worth continuing with covalent bond, because of course, why not?
yeah, I mean, you can try, but also I think it's important to understand what the inactivation in this case. Because for sure, if you understand the inactivation, maybe it's easier to target the functional group to immobilize. And in this case, we don't really know what's happening, especially with this oxidation of the DHA, because...
Yes. On that point, I would say check the pH, because the enzyme is inactivated very quickly when you change, and you are not working in good condition with this enzyme. Aldolase is better above pH 7, so your conditions were risky in a way, because you were obliged because of the CPO.
Yeah. Maybe if you increase the stability, the pH stability of CPO, you can increase the pH. Maybe it's another solution.
Maybe I don't know how. I didn't check my the time. Well, I have some other. What will you do in the future?
I'm looking for a postdoc here in Sweden, and I'm not sure in which field. I mean, probably related to this in enzyme immobilization or maybe kinetic modeling, but I'm not sure because I also I like to do some genetic modification of enzymes. I have background in biotechnology, but not really experienced in that, so I don't know. But I'm looking for.
Yeah, why not? Because you would add another competence on your another skill on your CV. Okay.
That's a plan, but we'll see.
And well, you did a lot of experiences, a lot of work, and so on. So, what would you say to the? Imagine, I don't know if it's the case, but if there is a student continuing this subject, what?
Yeah, there's one.
Okay, good luck.
Yeah, I haven't already talked to him, but my point is to make effort in this FSA inactivation if they want to continue with this work.
But maybe not only the FSA inactivation, maybe also the yield of aldehyde is quite low, so it's not a good starting point.
Yeah, but it's a problem of selectivity of the enzyme. So you can also use another enzyme in the system. I mean, I'm not sure if it's this system. I won't recommend this system for this. If I would if it's coming.
Okay, thank you. So now we have to stay. I mean, non-public audience. Oh yes, the question. Yes, I forgot that. Sorry. Do the doctors from UAB have some questions? No. Okay, so then.
¿Qué pasa? Cállate.